so what the title means, briefly, is that when you write a probabilistic program, you need to perform Bayesian inference to obtain the answers you're interested in. And in practice, the way this usually happens is you run some fancy approximate inference algorithm. So what we're doing in this work is providing a semantic account that corresponds to an actual algorithm that you're executing, rather than some sort of mathematical object that's not tractable to compute. So the way I'm going to do this talk is I'll start with a rather lengthy introduction to the problem so that I'll be able to state precisely what our contributions are, and then I'll tell you how we did it. Okay, so this is a very simple example of a probabilistic model written as a program. This is a typical example used to teach Bayesian inference. So what we're trying to model here is we have a lawn that can be wet or not, depending on whether it rained or whether or not you had a sprinkler on. And what happens here is we're observing that the lawn is wet, and the question is, well, what's the probability that it rained? So the way we construct the model is we specify some prior distribution over the fact that it rained, which in this case is Bernoulli 0.2. This means that it rains with probability 0.2, it doesn't rain with probability 0.8. Similarly, there's a prior for whether the sprinkler is on. And then we have a large lookup table that tells us the probability of the lawn being wet, conditionally on the rain being there or not, and the sprinkler being on or off. And then we score the program by the probability of the lawn being wet, which corresponds to the observation that the lawn is indeed wet, and then we output the value for the rain. So the way the inference problem amounts to enumerating all the possible execution paths of the program, computing the relative weights, and then summing the relevant terms. In particular, a program corresponds to a normalized measure over Booleans, and you can observe the true value is the value for the rain being true is 0.2, which is the prior probability, times the score. This is an expected value of the score under different settings of sprinkler, and similarly for false. So this is the unnormalized measure, and then if we want to obtain the posterior distribution, we just need to normalize it. So we compute this z factor, and then we divide mu's to obtain actual probabilities, and from this we can read that the probability that it rained is about 65%. Okay, so that's briefly how it works, but the problem gets very complicated when you have more sophisticated models, often with continuous variables, and there's a big integral you need to compute. So traditionally, how we do semantics for those things is if I want to do denotational semantics, I will interpret programs as measures. And there are some technical subtleties about how you construct suitable measurable spaces or how you make sure that they form a monad. But this is something that has been done before multiple times in various contexts. In this particular work, we're using a construction based on quasi-Borel spaces, which is a recent invention of my co-authors. This crucially allows us to combine continuous variables with higher order functions, which, as we know from the previous talk, is not a straightforward thing to do. Okay, so this is how people normally do semantics, but the problem is that this is just not tractable. So this measure object exists, it's well defined, but for anything but the simplest problems, I cannot compute it. So if I want to write a practical probabilistic programming system, I'm forced to do some approximate inference. So there are systems that try to do symbolic integration, like Hakaru, and that's precisely what you want to do if your model is such that you can solve the integral analytically, but most of the time it's just not possible. So you have to do some sort of approximation. And the kind of approximation we'll be looking at here is approximation by sampling. So a sampler, denoted by Q here, is just a tractable distribution over values x and weights w. And by tractable, I mean one that we can sample from efficiently. So think of it as a probabilistic program that doesn't have any conditioning in it. So you can just executed with a pseudo-random number generator, and it spits out the samples. And the standard way to approximate integral through the Monte Carlo methods is that if I have an expectation of some function under a distribution P, which is exactly this integral, I can approximate it by taking the weighted average of the function evaluations at the points sampled from Q. And pretty much any query you might want to have about the posterior distribution can be phrased as an expectation of a suitable function. Okay, and an important notion here is that we say a sampler is correct when it is unbiased. And that means that the expectation under all possible executions of Q from this estimator is exactly the right expectation that we're interested in. So whenever I say in this talk that our inference algorithms are correct, I mean exactly that we obtain an unbiased sampler according to this equation. Okay, so how do you do semantics that support sampling? So this is, again, a fairly standard construction, is to have something where you interpret your probabilistic program as a function that transforms some source of randomness. So in particular, we take here as an example a list of a list of real numbers from the 0-1 interval, and then the function produces a weight, a value, and then the remaining randomness. This last element is just to make sure that these form a monad, so it's easier to write semantics like this. And again, this is something that has been done before. Mitch Wand, for example, wrote a paper where they used similar construction, and you can show that this sampler is correct by showing that indeed if you take the integral over all possible sources of randomness, then it gives you exactly the measure you would have obtained from the measure semantics. Okay, so that's what's been done before. Now the problem is that this is not the full story. And the reason is that such samplers as the one on the previous slides are very inefficient. And they're inefficient in a statistical sense, meaning that I need lots and lots of samples to get a good approximation of my posterior distribution. And often in practice, this means that I just cannot run it long enough to obtain a sufficient number to get a good approximation. So what I need to do instead is construct a more clever algorithm that will produce a different set of samples, better in the sense that I will not need as many to get a good approximation to the posterior. So that will make the problem more tractable. Okay, so now I can state our contributions. We have developed denotational semantics that actually correspond to such inference algorithms that people typically run in probabilistic programming systems. And our constructions have a degree of modularity, by which I mean that inference algorithms are composed from building blocks. And in practice, what you do is you don't have a one best inference algorithm, but rather you have multiple algorithms that are good for different problems. And what our construction allows us to do is basically mix and match those building blocks to obtain the different inference algorithms. So we can really reduce the effort required for proving their correctness. And the correctness in our framework is compositional in the sense that we have those building blocks. Each one of them is proved correct, and the correctness of composition directly follows. So there is no further proof that you need to do about the compositions. Okay, so let me give you a little teaser for what we have done. So this is a pseudocode for a sequential Monte Carlo algorithm. This is something that's fairly commonly applied in probabilistic programming. If you haven't seen this before, it may be a bit difficult to read, so don't worry if you can't really get what's going on here. This is a typical way in which this algorithm would be presented in pseudocode. So conceptually what happens here is you start by initiating n particles, and then your particles are gonna run through the program. So T indexes observations in your program, and I indexes particles. So at each observation, you're basically gonna update the weight of your particle, And when you've done this for all particles, you're going to resample, and you're going to repeat that for every observations until finally you have completed your program and you return a set of samples and weights. Okay? And I can show you that this is precisely the equation that defines sequential Monte Carlo in our framework. So you can very clearly see that this is, in fact, a composition of those conceptual building blocks. So we start by spawning n particles, and then this superscript .k means just a k-fold composition. So at each step, we resample, and we run the program further until it's done. Okay, and it is common for such algorithms to have a certain structure such that, for example, a variation of SMC called the resample move SMC introduces so-called rejuvenation steps. So it's almost the same. The only difference is this part here. So that after I have resampled, I'm gonna apply a rejuvenation kernel multiple times to each of the samples. And this is something that's used for statistical reasons so that I can obtain a better coverage of the space. And you can see that conceptually, this is exactly SMC, only I stick those rejuvenation steps in certain places. And in our framework, we can indeed recover exactly that structure. So the equation for resample move SMC is almost the same as for SMC. The main difference being this eta here. So eta is the rejuvenation step, and it's applied L times. Okay, so let me give you a brief explanation of how we have achieved this. So the approach we follow is we'll start with a model, which is the source code, and we want to obtain a sampler. And the way we're going to do it is to transform through a series of intermediate representations. So we call those IRs here inference representations, and the T's are inference transformations. So these are terms we have devised specifically for this paper, so if you try looking for this, you won't find anything in literature. But just so that you understand what I'm talking about. And what are the requirements we have of inference transformations? So of inference representations? Basically, those are things that look a lot like monads. So we require that they implement the monadic interface, but they don't necessarily have to satisfy the monad laws. And on top of implementing this interface, they need to provide an interpretation for the probabilistic effects. So sample here samples a value from a uniform distribution on the unit interval, and score just accumulates the score. So those four things are sufficient to interpret probabilistic programs using the inference representations. And this magical fifth thing is the semantics. So this is this maps the inference representation back to the true measure semantics. So in a sense, so this constitutes our notion of correctness, in that an inference representation still holds all the distribution about the program or about the posterior. So we haven't lost anything, we haven't made any approximation yet. In principle, we can still recover the true semantics. So on this picture, as we go through subsequent inference representations, we will maintain an invariant that if we applied this function to intermediate representations, at each step we would obtain exactly the same answer as if we just computed the measure semantics for the original program. And that gives us immediately the notion of correctness. So all we have to do is prove that the individual transformations preserve this invariant. Okay, and I should mention that the first four things will generally be easily implementable, while the M is just a mathematical object. So if you actually implement a system based on this, this isn't gonna be available as code. It's just a conceptual thing that we can use to reason about it. Okay, so I don't have a lot of time, but I'll quickly show you the way we construct the algorithms is by. Okay, one more thing I wanted to say is that there are two different notions two different dimensions of modularity here. One is that we have this sequence of transformations that can be composed, and the other one is that inference representations are themselves constructed by a composition of essentially monad transformers. So not only can I apply the transformations compositionally, the intermediate representations are also constructed in a compositional fashion. Okay, so the simplest inference representation would be the sampler, which is just a free monad over the sampling effects. I give you a uniformly drawn number from 0, 1 interval, and then you give me the value. Okay. And in order to implement or to interpret the score effect, we just add a writer transformer that accumulates the weight. So this is just going to multiply all the scores that appear in the program. And this weighted sampler corresponds exactly to the sampling semantics I have shown you at the beginning. Now, if we want something more sophisticated, we're going to need additional transformers. So for SMC, I need two things. I need a population, which is a collection of weighted particles, or weighted samples, and I need a suspension. So this is just a coroutine transformer, and what it's going to do is introduce a suspension in the program after every score or after every observations. And the inference transformations associated with these are defined abstractly in terms of the transformed representation. So I have a spawn and resample for the population, and I have an advance and finish for suspension. And we show that these are correct, and then we obtain the implementation of sequential Monte Carlo by composing these. Okay, I'm not going to tell you about the tracing transformer because I don't have time, but this is an additional step that allows us to do MCMC, and we can just plug it in to obtain the resample move SMC implementation. So all I have to do is just stick this additional layer into the inference stack. Okay, so in summary, what we have provided is denotational semantics that correspond to practical inference algorithms that you're actually going to run. And we have achieved a degree of modularity so that we can mix and match different building blocks, which is commonly done in the approximate inference literature, where certain Monte Carlo algorithms are conceptually explained as different building blocks put in various ways. Okay, let me tell you very briefly about related work. Well, there has been a lot of great work done in probabilistic programming, and I can't tell you about all of it. Let me just highlight some papers that attempt to use formal semantics to reason about correctness of actual practical inference algorithms. So the first to develop a semantic account of MCMC, something that corresponds to our tracing transformer, and there's a lot of technical differences between our work and theirs, but I'd say the most important distinction is that they focus on a single algorithm, while we provide a modular, extensible framework that lets you construct different algorithms. The piece of work most closely related to ours is this paper by Rob Zinkoff and Ken Shan, where they also compose inference algorithms as transformations of intermediate representation, but they focus on a somewhat different set of inference algorithms, namely the exact inference that you can do with symbolic integration. So what they do is they have one intermediate representation, which is Hakaru core, and then they apply a series of program transformations that they can show preserve semantics. This is great work and largely orthogonal to what we have done. So I think we can just combine the two to obtain an even better system. Okay, so that's it. Finally, we have a Haskell library that implements the constructions I have shown you, so you can actually write your models and run algorithms, obtain your answers. We have a few more Monte Carlo algorithms that I have shown you in this talk, so check it out. Let me know what you think. Hopefully soon we'll also add variational inference, and then we can do really cool stuff with it. Thank you.
Hey, it was a very good talk. Can you tell me an example of where those might fail the monad laws and maybe an intuition of why that's the case?
Yeah. So in particular, the population transformer, this is just a composition of a list transformer and a writer transformer. And this is known not to be a monad or not to satisfy the monad laws if the transformed monad is not commutative. And in particular, the sampler that we're using here is not commutative. So this fails associativity, but in a sense, we don't care about it because it satisfies the monad laws up to this semantics M. So it's still going to produce the right answers.
Okay, thanks.
This is the right distance. There we go. Okay. So this is really cool because you're continuing your previous work about layering these different kind of transformation steps as monad transformers, and it fits great in the kind of Haskell mindset, and great. My kind of high-level question here is, can this? So we saw Gordon Plotkin's talk yesterday about differentiation, right? And this is really, as you know, this is really important in the space, right? HMC and NUTS are two examples of, these algorithms that really require and utilize this automatic differentiation. So is there a way that you can fit AD and differentiation into this kind of framework?
Certainly. So you can definitely do it in implementation. There's no problem with that. How it fits into semantics is a different question.
Yeah.
So for the moment, I don't think there is a theory of differentiation for quasi-Borel spaces, although some of my co-authors are working on it. So perhaps that will be sufficient to prove correctness of these algorithms. Maybe Matthijs can say more about it.
But you would still need to, you have to change your alpha type even to kind of support the AD, right? So you have to kind of change the underlying, underlying functions. Real has to now all of a sudden become AD of real, and it's not even in your monads. Or is that not true? You really feel like you can, maybe the implementation even, you can put it into the monad transformers or something? I don't know.
So, well, you will definitely have to use some sort of monad transformer that augments this thing with the automatic differentiation stuff.
Mm-hmm. But you think it can fit into this framework?
I think it should work, yeah.
Okay, cool. Okay.
Two questions which may be related. You started off making a distinction between exact inference and approximate inference, but the notion of approximate inference didn't show up in the rest of your slides. Where did that go?
So on this diagram here, all the steps that we do up to IRN are exact. And then the last step, where you will only draw a finite number of samples, is where you do the approximation. So all the transformations are exact, but only in the final step, you will not take the full integral over all possible executions of the sampler. You will just select particular runs, and that's where the approximation appears.
So that brings me to the second question. If you can go back to the slide you left us on. Yeah, that one's good. Mm-hmm. What's the notion of equality there? Is it equality on a particular sample, or is it the equality after you integrate over all samples? Or something else?
So you mean here?
Yeah.
Yeah, so this doesn't even talk about samplers, because this works for any inference representation T. And the idea here is that this M is defined in terms of the semantics of T. So T corresponds to some measure. And what the equation says is that when you apply a transformation like spawn on resample, then the measure that your representation corresponds to doesn't change. So in particular, if you take T to be a sampler, then you would say that integrating over all possible runs of a sampler would give you the same result before and after applying the transformation. Though, of course, the samplers are different, so a finite number of samples will give you different results. Otherwise, there would be no point doing this.
How hard is it to prove things like that?
So these things are relatively straightforward to prove. The Metropolis Hastings one was a bit more involved. Well, we have a lot of machinery for working with quasi-Borel spaces, in particular an instance of Anders Koch's synthetic measure theory. And that says that, well, you can use all the familiar results and notations from normal probability theory. So these things are fairly straightforward to prove, I would say.
Thank you.
All right, thank you very much, Anna.